When we consider planetary atmospheres or stellar interiors in atmospheres, and we obtain an equilibrium solution of the density and temperature profile, one of the first questions that we ask is the profile stable or unstable? And by stable or unstable, we mean if I draw a temperature profile, so here I'm going to draw the height of the atmosphere and the temperature of it. If the temperature profile has some sort of shape to it, like this for the Earth's atmosphere, where we've got a troposphere, we've got a stratosphere, we've got a mesosphere, and a thermosphere, you might want to know, are these different temperature profiles, are they stable or unstable to fluid motion? And the instability that we care about here is convection, which we'll learn about once we have some more tools on hand to be able to solve this. We're gonna use some knowledge of convection to answer this question. And it turns out that temperature and density on their own are poor variables to consider. But there's a better variable to consider. So how's convection work? Well, if we think of the surface layer down here, the troposphere, which gets warmed up by the sun, if a region gets a little extra warm here, then this region, there's a blob of fluid here, and this fluid is hot, and so hot things go up. That's the basic idea of convection. Hot things go up and cold things go down. And so as this blob heats up and goes up in the atmosphere, the trick is that in a temperature-like sense, this blob doesn't just go up. So I'm gonna remove my labels for just a moment. I'm gonna remove these just so we can see where we're going to. So how does our blob evolve? Well, we learned that the temperature of a blob, d by dt of t, it scales proportionally to gamma minus 1 times t times the divergence of u. Okay, well, what about this divergence of u? Well, we know from the continuity equation for density that d by dt of the log density plus u dot grad, the log density, is minus the divergence of u. And if we think of, we're gonna do a little violence in the math here. If we think of slow motions where there isn't much time derivative of the density maybe, and we think just about the, so these are motions that, like subsonic motions with quick pressure equilibration. The divergence of u is given by the interactions between u and the large scale density. And because of that, if we plug all of this in, we'd see something like d by dt of t. How does t change as we move? This goes as gamma minus 1, so minus sign because of the minus sign of the continuity equation, minus sign of gamma minus 1. Oops, this should have actually been a minus sign here since I moved it to the right-hand side. So this becomes plus. This is gamma minus 1 times the temperature times u dot grad log rho. And if this is our stratification, and this is our vertical velocity, then this is going to be less than 0 because as you go up, the density decreases. And so for a positive velocity going upwards, things go upwards, they expand in the lower density and they cool. So I start with a blob down here of hot fluid, but as it goes up the atmosphere, it's going to cool. It's going to actually get colder and colder and colder. And the question in convection is, as I come up and I get colder and colder and colder, and I'm drawing it on an adiabat here, on an adiabat, which will make more sense in just a sec. Adiabat. As I go up, am I hotter or colder than my surroundings? Anywhere the blob goes up and adiabatically expands, here it's hotter than its surroundings, here it's hotter than its surroundings, here it's hotter than its surroundings, so it keeps going up. And then when we get to the stratosphere, now as the blob goes up and tries to adiabatically expand, it's now colder than its surroundings, and it falls down. Excuse me, let me make this a little clearer. I drew these lines vertically, but we really want to compare our temperature to the current level that we're at. So the hot blob, it's to the right of the temperature line. Here it's to the right of the temperature line, but over here it's far to the left of the temperature line. So this blob is actually cold compared to its surroundings, and it's going to fall down. So the troposphere, which is adiabatically stratified, hot things go up fairly easily, but when they get up to the stratosphere, which is stably stratified, they stop and they fall down. And I want to develop some of the intuition for when you're going to get one class of behavior or the other. And as you can see, temperature and density are hard because you need to know both the temperature profile and density profile to know what's going to happen. We're gonna consider instead what happens with a new variable. This is complicated further because there's an advective term here, right? There's a u dot grad t that we haven't kept in this analysis, and so you have fighting between the temperature and density gradients that you have to overcome. So there's a new thermodynamic variable that vastly simplifies this. I'll call it simpler, but it's simpler in terms of convection. So we're going to think in terms of entropy. Entropy, and in particular, specific entropy. The entropy of a per unit mass. All right, so for an ideal gas, the entropy is given by specific entropy is S divided by the constant heat at the specific heat at constant pressure, and this is equal to the log of P to the 1 over gamma divided by the density rho. We're gonna work in terms of differentials, and the differentials we're gonna work in terms of our gradients. So it's going to be easier just to hit this whole thing with gradients from the get-go and work in terms of the entropy gradient. And it's really the changes of entropy that govern fluid behavior. So we'll work with grad S from here on. Before we proceed, I'll note that this right-hand side, this is a dimensionless combo. Now, it doesn't look that way too right now because we've got p to some like random fractional power in a row, but it must be dimensionless because it's inside a log, and logarithms don't have dimensions. So that means that this is also dimensionless. And so what that means is that the units of specific entropy S, these have the same units as the specific heat at constant pressure. Ergs per gram per K, basically. How much energy does it take to heat up a unit mass 1 degree? Okay, so now let's do some ideal gas. Let's play some ideal gas games. So we've got S over Cp. So this is 1 over gamma grad log times the pressure minus grad log the density. And the 1 over gamma in the front here, this comes from the power p to the 1 over gamma, and the minus log rho, that's because we had basically rho to the minus 1, and we pull that minus 1 out front. Okay. Now, pressure and density can be good variables to think in terms of. I find temperature a little more intuitive, especially when thinking about thermal equilibrium. So now we're going to write grad S over Cp is 1 over gamma. And we're going to use the fact that this is an ideal gas to write this as grad log T plus 1 over gamma grad log rho. So these are our, this is our 1 over gamma grad log p using the ideal gas equation of state, and then minus, of course, grad log rho. And then if I combine terms, I get the following. Grad S over the CP's inside the gradient for this simplified ideal gas. So grad S over Cp is equal to 1 over gamma grad log T. And if I combine these terms on the right-hand side for density, this is a gamma minus 1 over gamma grad log rho. Okay. And this ends up being a very interesting and helpful identity for us. All right. So when do we get convection? We get convection if the entropy gradient is negative, and we get a lack of convection if the entropy gradient is positive. So if the grad S over Cp is greater than 0, then stable to convection. And when we're stable to convection, we actually get a class of stable oscillatory waves called internal gravity waves. And we get linear waves that can show growth and eventually nonlinear behavior, but we basically just have linear waves. And this is the stratosphere kind of conditions. Stratosphere. Okay. If grad S is less than 0, then unstable to convection, and we have convection. Unstable to convection. We have convective motions and convective instability. And lastly, if the entropy gradient grad S is 0, then we have the same entropy everywhere, and we call this adiabatic. So the same entropy everywhere. And this is basically what the Earth's troposphere looks like. This is also what the convection zone of the sun looks like, whereas the radiative interior is stable to convection, and so is the outer atmosphere of the sun. So those are some different places that we see different types of stratification. Now, the fact that we have nearly adiabatic troposphere is a very special case. Same with the solar convection zone. This is usually this is the end state of convective instability. So as we'll learn at a later time, when you have instabilities, what instabilities tend to do is they tend to be powered by some quantity, and as the instability unfolds, they consume that quantity. They remove that quantity. So in this case, convection is powered by a negative entropy gradient, and as the convection churns and is nonlinearly growing, it acts back against that temperature gradient or that entropy gradient. It flattens it. Okay, so how do we use entropy to get some intuition for different situations? So the entropy gradient grad S over Cp, right, this was 1 over gamma grad log T minus gamma minus 1 over gamma grad log rho. And generally, not always, but generally, the density is a decreasing function of height. Grad log rho is less than 0, or unstable if you have an increasing density with height, unstable to a host of instabilities, and in particular to you're unstable to the what's called the Rayleigh-Taylor instability. Rayleigh-Taylor, of which we'll learn more at a later time. So generally the density gradient is less than 0. And because the density gradient is less than 0, that means that we really need to compare the temperature gradient. It's the temperature gradient that determines whether we're stable or unstable. Okay, and the temperature gradient, so the logarithmic temperature gradient, to remind you, this is the temperature gradient divided by the temperature. This can be whatever. As we saw in our drawing of the Earth's atmosphere, where it goes positive and negative. The gradient goes positive and negative as we move up through the atmosphere. Negative in the troposphere, positive in the stratosphere. All right. So this can be this can be less than 0. This can be 0. This can be greater than 0. It can be whatever. All right. So what do we do? Well, let's consider some different cases. If the log temperature gradient, if grad log t, if this is greater, and by this we mean that it's either less negative than, or that it's positive or 0 or anything like that. Because remember, this on the right hand side I'm writing down grad log rho. So this is a less than 0 quantity. If grad log t is greater than grad log rho, then the entropy gradient is positive. Grad s is positive. And that's because if grad log t is greater than grad log rho, so if we count them up here, so if grad log rho, this is minus grad log rho, this is a positive quantity. And so if grad log t is greater than grad log rho, then it won't cancel this out, or it will add to it, and that leads to this being a positive quantity. So if grad log t is greater than grad log rho, we have a positive entropy gradient, and that, as a reminder, that means that we have a stable stratification. If the converse is true, if grad log t is less than gamma minus 1 times grad log rho, then grad s will be less than 0, and this is convectively unstable. So this is unstable, and there's convection. And then lastly, there's the special case where the grad log t, where the logarithmic temperature gradient is equal to gamma minus 1 times grad log rho, and in this special case, grad s is equal to 0, and we have an adiabatic gradient. So this is the characteristic gradient of places where convection has acted to smooth out a large-scale gradient of entropy.